Hello, everyone, and thanks for staying until the very last presentation. So I got promised by Tim and Marty we have the full half an hour, so we're going to use it. Just joking. So originally this talk was supposed to be by Nikolai and myself, but Nikolai can't make it. So Sebastian is going to impersonate Nikolai, and I will be the guy from AMD you maybe have seen before. And we'll talk a bit about RDNA3 and how Vulkan allows you to use a new GPU. And the idea is to just give you an idea. It's like, okay, the new GPU comes out, people want to use it. What does it actually take to get access to those new features, and how do those things happen? So RDNA3, so how many of you have one? Oh, very good. Our sales team is working. Excellent, keep buying. So RDNA3 is our latest flagship GPU. So that's the diagram I shamelessly stole from marketing. It's a huge chip. I mean, you can see tons and tons of blocks. Someone has spent a whole day in PowerPoint to make this. And today we'll talk a bit about how you can use those blocks here and light them up so you can use all the power and heat your room while you have no gas here. So the first thing is the shader core, because that's the block which is repeated most often on the chip, and that's the one where most people are most interested in. So the shader core, that's how it looks like in hardware. So you can see there are a couple of schedulers, there's like vector registers and whatnot. And there are new things like matrix acceleration. There are new data types supported in the shader core. There are new instructions coming, atomic flows, for example, combined min-max and whatnot. And if you look at this, some of this, when I zoom in, the shader core has changed in 3 ways, basically. So some of them we have changed the ISA. I mean, we regularly change the ISA, introduce new opcodes. We have the secondary ALU and whatnot. And those things are actually automatic for you. So there will be a compiler update coming out eventually, or there is already a compiler update in this case, where those features get enabled and you don't even see it happening. And Sebastian will be covering this in the second half. Like, give you one example, like how do you enable actually a new opcode? Because it sounds like, oh yeah, you have a new opcode, 5 minutes of work, it's running. But it's actually quite involved to like even get a simple new opcode enabled. And then there's another thing where you actually need an extension, right? There's functionality which is not universally available. I mean, there are a bunch of new GPUs which have this particular feature, and there's like nothing in Vulkan. When we sat down and designed like Vulkan 1.0, like nobody knew this feature was becoming. So there's an extension, and ideally, when you have multiple vendors supporting the same extension, you will get an EXT or KHR extension. So that always takes some time, because typically everyone wants to have the hardware in hand and then design an extension which works across everyone's hardware. And that's like floating point atomics would be an example here. And then there's other stuff which is pretty new. Like everyone has it in some shape or form across all the vendors. And now we need to actually come up with an extension first, right? We are still working on, okay, what's the behavior on across all of those things, and like how do we expose it the best way? That's, for instance, like the matrix multiply and the whole machine learning stuff, really. Because if you look at it, it's like machine learning is taking off. Everyone loves to do matrix multiplies. I mean, like there's no tomorrow. And you want to make sure when you make an extension that the next thing you do is not matrix multiply 2 and the next one is matrix multiply 3, right? Because, I mean, even though there are only so many ways to multiply a matrix, you still want to be as future-proof as you can. And trust me, if you look at the machine learning landscape, I mean, there have been never so many ways to multiply a matrix as there are today. So it's incredible. And then there are other things in the shader core where we keep flexibility, and it makes sense to select between things. And the great thing about Vulkan is it's like in many cases you have those controls already in Vulkan. So one example I want to give here is, so the AMD GPU core has 2 different execution modes, one called Wave 32 and one called Wave 64, where basically you emulate subgroup sizes of 64, 32, and they execute on the hardware. And there are cases where Wave 64 is beneficial. So we have like super ALU dense code and then float 16 in there, and then Wave 64 may run faster. And then there are cases where you have like super divergent code, like half your wave is dying quickly and so on, and you don't want to run very large waves, and you want to have Wave 32. And usually this is another case, right? We have some functionality, a couple of vendors have this functionality. How do we access it? And thankfully, Vulkan already has an extension shipping for years actually now, which is now even part of Vulkan 1.3 core, where you can let the driver choose between them. Because when originally Vulkan was designed, there's a feature called GL subgroup size in Vulkan, and that has to be constant, so that you have to settle on one number, so it's 64, you get there. But there's an option to opt in and give the driver more flexibility and actually choose the size yourself. those are the things, for example, where Vulkan already has provisions for flexible hardware coming out and then having this control, and you can just exercise it however you want. So that's the shader core. Then there are other exciting things people like. We saw ray tracing before. So RDNA3 has been also doing some stuff on ray tracing. And the great thing is, like, there's nothing new to do here. I mean, we had the presentation from ARM. Everything you saw in there just works here as well, because it's a standard. Standards are supported by everyone the same way, and that's the great thing about Vulkan, right? It's like nothing to do. You just take it from one to other, and also from RDNA2 to 3, it just will work and continue to work using the same stuff. Then we have memory. I think that's a pretty exciting one, actually. So as you may have noticed, I mean, GPUs are getting more and more memory, like tens of gigabytes of memory these days. And there is this thing where when you went yesterday for dinner, there's a bar usually, right? And there's sometimes a very large bar, or a resizable bar even, right? Where you can make it even bigger as you go ahead. And that is also the case on your CPU most likely these days, right? So back in the old days, there used to be a very small bar, like 256 megabyte, and everything you wanted to shuffle on the GPU had to go through this one. That becomes very inconvenient if you want to have, like, I want to have everything bindless, I want to have everything permanently mapped and so on, right? Because 256 megabytes, where your frame buffer is 20 gigabytes, is like it's 1% is mapped constantly. And over the years, there came this feature, which is called on AMD, it's called Smart Access Memory, which allows you to resize this area to the whole GPU memory, actually. And the first API to support it was Vulkan, because when we designed Vulkan back in the day, we had good insight that this might be a feature coming one day, and then our memory heaps, which can expose this functionality, so you just have the right flags, and now suddenly you have a heap which says, I'm device local and CPU accessible, and I'm the size of the whole GPU memory. And there's nothing you need to do in terms of like new extensions, wait for new functionality and whatnot. You just plug in a new GPU, turn this on in the BIOS, and everything works. And even better, there's middleware. If you use something like VMA, you just don't even notice. It just magically works, thanks to Adam's work over there. And if you want to know how it works, then just ask him, because I don't know. I just know it works. And then finally, there's video encode, decode. So that's a very interesting feature many people like to use. I mean, right now, you're running a video decoder and encoder probably to send this video stream around. And everyone has been innovating in the space of video encode, decode recently. We have new formats and whatnot. And it's also great news here that Vulkan has also provided a cross-vendor extension now to access all those video encode, decode units, multiple queues and whatnot. So you have this like separate extensions, as Tony was previously explaining. So you have like encode, decode, the individual formats and whatnot. And all of this is shipping today on the GPUs. So that means like if you want to do a video, everything you need is available on Vulkan and on modern GPUs. You can use all of it. All of it with one exception. So AV1 is not available yet. So obviously people are working on it. And you can read this blog post if you want to see like how someone actually got it already running and follow the development along. All right, and then we go back to the shader core. So we have new instructions. And as I mentioned, not every new instruction has to be visible to the surface to the high-level code. The surface to the high-level code means you don't get a new intrinsic which says AMD foo, and then you can call this new function. It's just some function you had previously happens to run faster now. And we will walk you through one example, like a very simple example, just to give you an idea of what it actually means to enable a simple new opcode and how long it actually takes. And this is where we will spend the next 25 minutes. So let's go, Sebastian.
Okay, let's take a look at an example. So just a single line, we have maximum of a value and 0, which clamps it to 0 or above, and a minimum of the result of that and 5. So in the end, our result will be, whatever value else, it will be between 0 and 5. So if you wrote that code in a shader so far, if you can raise your hands. That's a couple, quite many. So yeah, you see, that is quite common in shader code. So for GPUs, it makes sense to optimize it in some way, so it doesn't take a second to do that. And yeah, if you look at the RDNA2 series, that takes just a single instruction in ISA. You have a vector instruction that is a median of three input values, and well, v1 is the output value, second v1 is the input value, and we take the median of that value, 0 and 5. Well, that's nice. Now let's change one thing here and make that upper bound a variable instead of a constant. Oh, now it's two instructions. Well, that's not too great. And now we'll dive into why that happens and how that is fixed. So looking at the instruction first, what does it do? Well, it computes the medium. We have a lower bound and an upper bound, and we have three cases. Our value can either be in that range, above that range, or below that range. And the median takes the middle one, all of these values, and returns it. And we see it either returns, well, the value in the lower bound or the upper bound, and it gives us exactly what we want. Now, then why doesn't it work if we replace the upper constant? Let's look into how the compiler actually does things and how we end up with a median instruction. So in the high-level shading language of your choice, you write that code, but that's not what the driver actually sees. You first compile it to SPIR-V, where it will be two instructions, assigned maximum and assigned minimum. And that's what comes into the driver. Now, our Vulkan driver is based on the LLVM compiler, so we first transform that into LLVM AR, where we get, again, two instructions. And as you know, compilers do as many transforms on your code as possible, and in the end, they will somehow end up in ISA, and then we're finished. So one of the languages in LLVM is the so-called instruction selection directed acyclic graph. And here we still have two instructions. Now there's some transform in there that makes it end up at just the single median instruction. And then there's two more intermediate representations, and finally you end up in assembly. And now we got to look at the part that actually does the work, which in this case is called instruction combiner, because, well, it takes two instructions and combines them into a single one. So that code is quite readable on the high level. So you just have one function that gets called for every single instruction in your code. And you have a large switch case statement that goes over all opcodes that could possibly exist in your code. And you see there are some case statements for maximum, minimum, whatever you may have. And then we call into a helper function that then does some checking. So at the bottom, you see the if statement that checks, do we have a minimum instruction? And is the first argument to the minimum instruction a maximum instruction? And there's one special case. If that max instruction is used more than once, then we don't want to optimize. If it's only used once inside the minimum, then we call into yet another helper. That's the bottom of the pipe, finally. That is the code that actually creates the median instruction. And yeah, creating the instruction is not that difficult. The larger part is checking that we actually are allowed to do that or can do that in the compiler. So first we check, are the two bound inputs, so the second argument to the minimum and the second argument to the maximum, are they constants? And if they are not, then we bail out and just don't optimize anything. If they are constants, then we check, is our upper bound actually larger or equal to our lower bound? At that point, you might get a hint why we don't optimize if we don't have a constant upper bound. Yeah, and if all these conditions are fulfilled, then we just create a median instruction and are fine with more optimized code. So why do we have these checks? So we have these three cases where the median always works. But there's actually three more cases that we left out. That is, if the upper bound is actually lower than our lower bound. So they're kind of swapped. And let's see what happens if we execute the max on value and our lower bound. So lower bound is the right one here, that's the 0. So taking the maximum of value and 0 will end up at 0 if our value is lower than 0. Then taking the minimum of that result and our so-called upper bound variable, which is negative, will, well, end up at the negative number. That is not the same result as we would get if we took the median. So yeah, we don't have constants, and now there are suddenly cases where it doesn't work, where we can't just take the median. Yeah, and if you see the code, as a shadow developer, you probably know that this is just a clamp. And actually, the OpenGL clamp intrinsic is defined to just do maximum and minimum, so it's basically the same code. Still, as a driver, we can't optimize it to the median because there may be some cases, or there sure are cases, where people don't want that and actually rely on the behavior that you can have a maximum and a minimum that will not be equal to the median. Yeah, no, that would be a sad story if I just ended here. But luckily, we're hardware developers, so we can change what actually happens or what we can do. So in the RDNA3 series, there are 2 new instructions that handle all the corner cases. So they just execute first maximum, then minimum, or the other way around. And these instructions exist in variants for unsigned integers, signed integers, 32-bit floats, 16-bit floats. And yeah, if you compile the same code for an RX 7000 GPU, you will get 1 instruction again. Nice. Yeah, that's what it takes to optimize a single cycle. And that may not sound much, but if you do that every generation, and you do that for a dozen or some dozen instructions every time, it does add up. At some point, you are faster, noticeably. Yeah, that's what we do with new chips.
All right, thanks. I mean, and that's a good example of it. Like, so this is like a super simple thing, right? I mean, you can already see like even the super simple thing. Okay, you have to be in a compiler, this and this condition, blah blah blah. If you want to expose like an actual new instruction like to the user, like this work just like 1 magnitude more work, right? And if you want to have like a large extension, we want to do machine learning on GPUs, you can imagine like how much more work it is, right? But that's like just to give you an intro level here, because anything where we would have to expose an opcode and then tell you how we go through GLSlang, DXC, and then SPUV extension and whatnot, we would be having a 3-hour talk here, right? So to conclude this talk here, and we will be 1 minute past time, so I think we deserve something here afterwards. Thank you. So the great news here is like Vulkan exposes most of the advanced features of RDNA3 already, right? And that is true actually for modern GPUs in general. I mean, like Vulkan is super quick on exposing like all the functionality, because either there's a vendor extension, it was already provisioned into Vulkan because it was more flexible in some ways, or because it's like fairly easy to get industry alignment across the couple of people shipping new drivers. I mean, like looking back at the history of Vulkan, I mean, I think we have been doing an amazing job with EXT and KHR extensions. They're getting across the industry alignment instead of having like 5,000 vendor extensions shipping around. So hopefully that's also your perspective on it, because obviously I'm biased. And then the interesting thing is like very large features also ship in Vulkan in a reasonable amount of time, right? I mean, video encode, decode is huge, right? I mean, like there were like dozens of man-years of effort went into that extension, and it's still coming out fast enough and then to be actually usable for interesting applications. And in many cases, like new hardware appears and it just works, right? As long as you keep your drivers and everything updated, because like the way Vulkan was designed is like it allows for a lot of hardware innovation still, right? I mean, if you remember like the old days of like OpenGL, I mean, like obviously you can implement like the hardware can dramatically change under OpenGL, but it's like, does it actually go much faster in this sense, right? Because sometimes like you just can't scale with it. But for Vulkan, I would say we really achieved that, right? We have an API where the underlying hardware can change a lot from one generation to another, and your application benefits the same way, right? Because you're not bottlenecked in CPU, you're not bottlenecked on various things which are like hidden under you in some layer and whatnot. And that's it. That's our talk. Thanks for listening. We have probably time for one question.